All right, so let's go ahead and do one more thing. So as in every good problem, what happens if we, so let's say, okay, we tested positive and the doctor says, okay, don't worry, you know, we're gonna take another test. It's a different kind of test. It's also 99% accurate, but it should give us different results. So, you know, where we should like, basically we're taking a secondary test, right? And it has the same exact, you know, like accuracy, you know, all that stuff and everything. So now it's a new thing. Now we have the situations like, hey, oops, I'm trying to draw here. We have the situation where the probability of us, let's call it C just to make it easier, right? Given C, where C is that we tested positive, right? But we already tested positive once already, right? And then we have, this is not the best idea. This is C where we test positive again. So we take another test, we go in and we test positive again for the secondary test. Okay, so we tested positive twice right now. So this C event is that we tested positive twice. Okay, does that make sense? Okay, so we tested positive twice and this is us being sick. Okay, so that was still like event A. This would still end up being Bayes' theorem. We can write the whole Bayes' theorem equation here, right? Basically the likelihood and then our posterior, or sorry, our prior. So our prior is what we found earlier. So our previous prior was the probability of us being sick, right? Which all we knew was like, well, what are the chances of us being sick in the whole population? Well, that's going to be, you know, that was like 0.001. Now our new prior is, well, we tested positive once already. So we know we're at least 0.0098, right, percent of actually, or 0.98% actually sick with this disease, right? So it's gone up a little bit, but not that a huge amount. And the likelihood is still like that same value if we were to look at like the probability of us like testing positive again. And so now we have this put in here. And the idea here is that we can keep updating our prior. So this is going to be our new posterior. And our prior is going to be our old posterior, right? Our posterior that we just found, our 0.98%. Okay, has everyone followed me on this guy? Okay, so now the scenario goes, okay, we tested positive once, right? But it's a very high chance, almost 99% chance that we're still healthy, right? So only less than 1% chance that we're sick. But now we test positive again on a new test, an independent test. What are the chances of us now actually having this rare disease? And so I'm going to ask you guys, now that I got to ask you guys once before, is what's the probability of us, of you actually having the disease now that you tested positive twice? And the same like accuracy holds. Like we're going to pretend this is an independent test, but it also has the same 99% accuracy. Any guesses? Remember, it went from like 0.01% to like 1%, right? So what do we think that this chances are? How likely are we having this? How likely are we going to be sick?
I think it should be high, no?
Yeah, so give me some numbers. You know, it's okay. We're gonna do the math, but like, when you say high, like, how high you think?
Very high. Like, you know, if it's test positive twice in a row, it's got to be like, you know, like 99%. Like, you know, something high. Yeah.
Okay, so like really high. So like, oh, like it's almost like certain that we have this disease. Like you said, like 99% or something around there.
Yeah.
Okay, cool. All right. Anyone other guesses? Now I made you guys all scared because I gave you guys like that really extreme answer before. Let's hear another guess. Any chance? Like, what's your intuition? Like you don't have to worry about Bayes. Like, don't worry. Like, Bayes might not be super intuitive by itself, but like, what's your intuition? You test positive twice, assuming that like you saw what happened with the first positive.
I mean, it should be more likely now that you're sick, but you're still dealing with a huge population. You're still getting thrown back into the population, right? And then getting tested again. So there's still a good chance that you're part of that population that you know is 1% of the time gets misdiagnosed, right? Mm-hmm. So I think there's a better chance of that the test is right, but you still have a great chance of being found to, you know, to be tested wrong.
So higher chance, but not necessarily sick. So maybe like 40% chance of being sick. Is that kind of, I'm just trying to put numbers onto like what we're verbally saying.
Well, if you want to throw it out, I'll take that. I'll take
Okay,
whatever,
all right.
you know.
Okay, cool.
So we can move on.
Yeah, so I think that's exactly what we're thinking, right? Is that like, okay, like, you know, I think this is my real feeling too. It's like, okay, it must be like a little bit more, but not too much more, like, you know, like we saw before. And I can actually set the prior probability sick, and since we made that function, we can just put this in there and we can actually see 96% chance of us actually having this disease. And so I think the big thing about it is kind of like what Alvaro was saying, you had the concept down, but the numbers can be kind of tough for us to kind of see this. And the way, if you guys remember, I'm gonna get these numbers wrong because I don't remember exactly, but I had like 9,900 people were like in that group A who were positive but sick. And they had something like 99,000-ish. I think that was about right. The thing is that these are our new parts right here, but now we're gonna split them again. And so what happens is that 99% of these guys, so nearly 100%, I'll just say like about 9,000 people are sick who test positive again, right? Because we're only testing these guys. And these were our healthy people who tested positive, but only 1% of those people are gonna test positive now, right? So what is that, 1%? So that's like 990, right? So like you can still see, like there's actually a big difference. Now you are more likely to be in this group here because there's less people basically breaking off. You could do the same thing visually, but that's kind of like the way I think about it. So again, the real reason why I'm kind of showing this, like Bayes can be kind of like a little unintuitive, but it does kind of make sense when you kind of like think about like what the concept is. It's just that the numbers I think sometimes can be really tough, especially when you get these really extreme values. So basically that is Bayes' theorem and everything. And we'll actually talk more about this for something called naive Bayes, which is a machine learning algorithm. It's actually naive Bayes is really useful for, was a really big step in spam detection, where basically you can use the fact that these things are independent, which is not 100% true in naive Bayes, like, which is why it's naive. We can assume these things are independent from each other and say, well, what's the probability of us having spam such that these words? But we'll talk about that in mod 3, a little bit like 4 or 5 sections into the next module. But I thought we'd talk about this before we move on and, you know, talk about just linear regression for the rest of the time. Okay, cool. All right, everyone. Well, I know I kind of went a little over, but I think it was a good amount of time. Hopefully you guys felt that was useful too. And then just know tomorrow we will again start at 5 p.m. Eastern time. It'll go for an hour and a half. And that's just to give us enough time to go over polynomial regression, interactions. We'll go over that relatively quickly. I think, you know, it's not too much a big step. And then we'll kind of talk about Kaggle and I'll kind of walk you guys through what this might look like. And I think that'll be good practice for, you know, when you guys get into your end module project focused on regression or linear regression. Okay. All right. Well, I'm going to stop recording here.